FIFA. You could probably play soccer with it and be fine.
You have a very hard time playing soccer.
I'm going to tell you, don't eat this stuff, but I don't think it's especially radioactive. Just saying. That's some of the most radioactive stuff we have on the planet. Because these are way overloaded with neutrons. So these will cook for many, many years. They stay hot. They stay radioactively active. Pieces keep falling off for many, many, many years. So when you make radioactive waste, you got to store that forever. High-level radioactive waste is really, really scary. Anybody want to talk more about the products of fission, what we call the decay products? Yes?
So is it inefficient then to try to use the waste to make more energy?
Yeah, because remember that's hot, but that's not fission. Like the molybdenum will stay molybdenum and it'll just spit off neutrons. Ditto with the tin. They're not fissile. They're just radioactive. Big difference. Fission, the splitting of the actual nucleus, gives you the energy. This just gives you like lukewarm radioactivity. So like, oh, that feels good, but my hands are melting.
Why exactly does the radioactivity harm living things?
Because it disrupts bonds. I don't really understand the details of this. To be perfectly honest with you, radioactivity is kind of over my head. But a lot of times mass and energy are kind of related. And so the subatomic particles do have energy. And so when they leave, I don't understand. I know that destabilizes bonds. In you and me, like 99% of our bonds are useless and they don't matter. But every now and then, you can tweak a bond in DNA that's effective. We could mess up 99.999999999% of all the chemical bonds in your body with no impact to your system. Because any single cell is always disposable in your body. But if we tweak one of the DNA bonds that regulates growth of a cell, and it happens to tweak that bond in the direction where you get runaway growth, now you're screwed. That's the only real problem. Like the cancer thing, cancer is just uncontrolled growth. The tumor is too many cellular divisions from one starting point. It wastes your energy and it might mechanically clog your functions.
What about like immediate exposure to radioactive? Like,
Then it might be too much energy, so you can get a radioactivity burn. Like your skin melts off. Yeah.
I thought you said there wasn't that much energy in it.
Yeah, it's like somewhere in the middle.
So like too much for humans to handle, but not enough for us to actually use that.
Right. It's not to boil water, it might be enough to like give you the first, second, third degree burn. I don't know, man. And by the way, ask a real chemist, I made all of that up. 100% made up.
You said that tweaks the DNA to cause absence growth, and that's what DNA is? Or cancer?
Yeah.
So why do they give you radiation?
Treatment?
Yeah.
To kill cells that they don't want there. A lot of times, the same radioactivity that tweaks the cellular function can be used to turn off the bad cellular function. So you kill the tumor with the same radioactivity that made a tumor. Because really the odds of making a tumor are really slim. Most of the damage would kill the cell, but not result in unregulated cellular growth. So we use radioactivity because supposedly that has more chances of killing the tumor than of making another tumor.
Okay, so cancer is just kind of a weird thing. It just kind of starts.
Yes. That also happens for a zillion other reasons too. And there's radioactivity all over the place, and so this just raises your odds. Great. Okay. Anybody else on the chemistry thing? Because watch this. If my room was full of firecrackers and some kid walks by and throws in a lit match, one firecracker would ignite, pop, and when it pops, it would shoot sparks, and those sparks would light the other firecrackers, which in turn would explode and light more sparks, which would light, and eventually this whole room would blow the ceiling off, the roof off, right? Yeah. Techo and techo. In Spanish, they're both ceiling roofs, so I always get it wrong. Okay. This is the scary part. the energy we want is how we're going to boil the water. But these are scary because if they find more uranium-235, then we'll get 2 more explosions and double the energy with more neutrons that can keep going. So imagine 1 unit of energy is followed by double the energy, is followed by double the energy, is followed by double the energy, is followed by double the energy. Yeah. It's followed by double the energy and double the energy. And so eventually you just get too much energy and your stuff melts.
Sounds like unlimited energy.
The nuclear meltdown is when one of these neutrons just becomes too many and you've got too much energy to control, and then literally the steel and concrete start to melt because it's that hot.
Yeah, I thought we designed the pellets to make those two reactions.
We did.
Yeah.
And so we know that there are a lot of these atoms, and we have to control them somehow. So,
Water.
the next thing I need everybody to see is the first of the 2 engineering challenges. There are 2 challenges in taking this as a way to boil water. Challenge number 1 is controlling the reaction. If we could absorb the neutrons, we'd be fine. Right? Like stopping the sparks in my pile of firecrackers. So look up here. There's these things called control rods, which you can push into or out of the reactor. And the control rods absorb neutrons. Because boron, the moderator, is a neutron absorber. I don't know why, ask a chemist. All I know is boron absorbs neutrons. So like stopping the sparks in my pile of firecrackers, when you put boron into the reactor, the heat starts to go down because you're getting less and less reactions. This make sense to everybody? When somebody says, hey Tyler, can you turn on the nuclear power plant? We need more electricity. What Tyler does is go, sure. And they take the control rods out. And then the decay of these spits out some neutrons. And once the neutrons get started, the heat starts to build. And when you start to get too hot, you just have to put the brakes on it. A nuclear reaction is like a car going down a really big hill. You just got to give it some brakes every now and then. So when it starts to get too hot, you just drop in the boron. And then when you slow it down,
You have to replace the boron after a certain amount of time.
yeah.
So what happened if you know
That sounds like an awesome job.
I'll tell you what happened at Chernobyl as part of my slideshow, and 3 Mile Island, and Fukushima, but that's Wednesday.
Why do we use water as an antidepressant and not like some of this fluid or something?
In many cases, we can, and we'll talk about variation in these reactors soon. But I want to make sure that everybody caught the detail because I'm kind of racing against the clock. I want to make sure that everybody caught these details. The control rod, made of boron, absorbs neutrons. Because it controls the reaction, that's called the moderator. Controls the reaction. These are all vocab terms if they're underlined. I know there's a lot of underlining. Now, second engineering challenge is controlling all that heat. We control the neutrons with the moderator. We got to control the heat. And that's all this crap. All this engineering is just heat control. So we will do this next, but I want to see if there's anything I can clear up in your misunderstandings before we do the reactor.
What do we do with the water that's in there?
It is radioactive waste, and it's high-level radioactive waste.
That sounds like really bad water.
It is.
Should we just like keep that in there for as long as possible and then store it?
And then store it. You know, there's this one funny principle. Yeah, exactly. Put it in minority neighborhoods. Label it kids.
Are we saying some high radioactive water?
No, but we've talked about that.
Well, actually, I think the pressure of the bottom of the trench is great enough that it will strip the stuff that we put down there of its radioactivity. But we can't do that because of like 50 international treaties.
So less circulation of water.
Yeah.
Okay. So one thing that I wanted to clarify about this, there are two engineering challenges. The reaction control, which is just absorbing neutrons. That's like, we're done with that part. But now the heat control is going to be a big challenge. Remember, from here out, the turbine, the steam turbine, generator, electricity, that's like every other power plant on Earth. The only secret is, can we move the heat away fast enough to keep the stuff from melting? And interestingly, the only nuclear disaster in the United States was a failure of water pumping. All the engineering was fine, we just couldn't get the heat away enough. And 3 Mile Island happened. In Fukushima was probably the worst ever nuclear disaster. Used fuel rods, this stuff, ran out of water because the typhoon shut off the electricity that was used to keep water on the spent fuel rods. I know, dude, it's like the dumbest engineering ever. Plus, it was on top of the building, so they were in pools, and the building shook from the earthquake, and so all the water sloshed out because they didn't have a lid on it.
What the hell, man?
Oh, really? Too bad nobody thought of that. Okay.
Way to go,
So let's talk about heat control. Everything you see here is heat control. I want everyone to know where I'm going with this first. Heat control here, watch me. We got to get this heat, that red arrow, all the way out into the air. When you guys watch The Simpsons and they show you the radioactive steam coming out of the nuclear power plant, you should realize a lot of steam comes out and it's not radioactive. I've been in those. It's really comfortable. It's like a sauna. I'm not kidding. They're really cool. You can walk in at the bottom. You see how it's elevated at the base? It's all airflow. It's like on piers, so it can suck in cold air. And they have misters in the top and all these pipes on the inside. And the misters hit the pipes and go and take the heat away from the pipe. And it literally feels like a sauna, and birds build their nests in there, and they're kind of cool. And no radioactivity, don't worry. There's like zero radioactivity. It's just steam. Okay. So I'm going to move my heat away. That's my job here. So I'm going to get rid of the heat. Okay? That's 3 Mile Island. That is a mile. That is an island that is 3 miles long. Okay. So watch me. This is called a pressurized water reactor. That is 70% of all reactors on Earth. Every one in the United States is a PWR. China is hoping to make all their nuclear reactors PWRs. Canada uses a different kind. France has the most of these. I believe so. They're extremely common. Chernobyl skipped one of these steps. We'll talk about Chernobyl later. Now,
those Russians.
Too many interruptions. I'm sorry. I do have to go against the clock. Look, heat control has 4 points of heat exchange. Coolers at the rod, steam generation, condenser loop, and cooling tower. They're marked with X's. And I'll tell you how this works. The primary cycle is pressurized water that goes through the reactor core. It's pressurized, so it can't evaporate. That water gets really, really hot. It's got so much pressure, 2,200 psi. If you guys know, that's a lot of pressure. That water gets to roughly 600 degrees Fahrenheit and doesn't evaporate because it's got so much pressure on it. So watch. Cold water comes in. It's called the coolant because that cold water takes the heat away from the fuel rod, this heat. Okay? Now it's hot water. So that's 1 point of heat exchange. Where you cooled off the rods, cooled it. Everybody with me so far? This hot water will never leave. It's super radioactive. It was just tickling your